Section 4.1 is on indefinite integrals. What we're doing is it's really the opposite of what we were doing when we were taking the derivative. So now instead of having the function and us trying to find the derivative, you'll be given the derivative and you'll be trying to come up with a function that has that derivative. So in this case, if f prime of x is x to the 8th, we want to know what is f of x. So when we take the derivative, we subtract 1 from the exponent, which means that this f of x is going to have to be an x to the 9th. So when I take the derivative, it's x to the 8th. The problem is if f of x is just x to the 9th, I'd move this 9 out front and subtract 1 from the exponent. So right now my derivative would be 9x to the 8th. Well, to cancel that 9 out, we need a 1/9 right here. So now when I move this 9 out front, I have 1/9 times 9, which is 1, subtract 1 from the exponent, which is x to the 8th. Notice this isn't the only f of x that has a derivative of x to the 8th. 1/9 x to the 9th plus 1 also has a derivative of x to the 8th because the derivative of 1 is 0, or plus 10, or plus 100, or plus 7, or minus 3, or plus any constant. So if I have 1/9 x to the 9th plus any constant would have a derivative of x to the 8th. So we write any constant as plus c, plus a constant. That constant could be 0, and it could just be 1/9 x to the 9th. The constant could be -2 plus -2, so -2, and so on. The notation that we use to show that we're trying to find the what function has a derivative of something is called an integral. It looks like this. So the integral of x to the 8th, and then this dx shows you which variable we are integrating. In this class, that dx, this is always going to be the same as this variable right here, is equal to what we just found, 1/9 x to the 9th plus c. And again, that's read the integral of x to the 8th dx. So the power rule, which is what we're learning in this section, is the integral of x to any power, x to the n. So what we did is we added 1 to the exponent, so that's x to the n plus 1, and then we divided by this same thing, plus c. And this power rule will work for almost any value n. The only one it doesn't work for is -1, because that's going to make you divide by 0 here. So n is not allowed to be -1. There's a different rule if n's -1. That's not until chapter 5. Nothing you'll learn now. So example 1, most of them will look more similar to this. Like derivatives, if we have various terms with a plus or minus in between, we can just take the integral of each individual term and then add or subtract them. Also, if we have a constant out front, we can just take that constant times the integral of this to get the integral of this entire term. Now that only works if this is a constant. If we have two variables like x times sine x, where like if we were taking the derivative, we had to use the product rule here. You cannot just take the integral of this and the integral of that. That's something you'll learn later in section 4.5. So in this case, I have 12 times x to the 5th. X to the 5th is a power, so we can use the power rule. We are integrating, so we want to find something that has a derivative of 12x to the 5th. We add 1 to the exponent and divide by that same thing. Add 1 to the exponent, divide by that same thing. Here we're thinking, what has a derivative of -9? -9x would have a derivative of -9. Another way you could think about it is this is x to the 0. So when you add 1 to the exponent, you get 1 here. Don't forget your plus c. Simplify any fractions. So we've got 2x to the 6th plus 1x to the 3rd minus 9x plus c. And you can check it by taking the derivative and making sure that you get this guy up here. Move the 6 out front, gives me 12. Subtract 1 from the exponent. 3 out front, subtract 1. Derivative of negative 9x is negative 9. Example 2, first thing we're going to do, notice we have the 6th root of x. We can use the power rule there as long as we rewrite it. So the 6th root is the same thing as the 1/6 power. Secant squared x is not a power. It's not just x to an exponent. So for the trig functions, we need to think about our trig rules. So the derivative of sine x is cosine x. Therefore, I can undo that by saying the integral of cosine x is sine x. Let's see. The derivative of cosine is negative sine. Therefore, the integral of sine is negative cosine. So in this case, we want to think about the derivative of what is secant squared. And at one point you memorize these. They're on page 244 if you're not familiar, if you don't remember. But the derivative of tangent is secant squared. Therefore, the integral of secant squared x is tangent x. So when we go to integrate this, we have the integral of x to the 1/6 power. So we add 1 to the exponent. Adding 1 would give me 1 and 1/6. And then we divide by this same thing. So if I divide by 7/6, I'd have 1 divided by 7/6. Integral of secant squared is tangent x. We just said that. And 1 divided by 7/6 multiplied by the reciprocal is 6/7. So one thing you can do instead of dividing by a fraction, if you have a fraction here, is just multiply by its reciprocal. So best answer on this one, 6/7 x to the 7/6 minus tangent x plus c. Those rules on page 244 would be a good thing to refer back to and then memorize for the Chapter 4 test. Example 3 asks for the integral of 6/x to the 10th. We're dividing here, so we can't yet use the power rule. But if we rewrite it as 6x to the negative 10th, now we can. Add 1 to the exponent, negative 10 plus 1 is negative 9. Divide by that same thing. 6 divided by 9, we can reduce that to 2/3. So we've got negative 2/3 x to the negative 9th plus c. And you can either leave it like that, move the x to the 9th down to the bottom. And finally, example 4 asks for the integral of 3x to the 5th minus 2x squared plus 5 over x squared. Just like the previous example, when we're dividing, I cannot just take the integral of the top and the integral of the bottom. With derivatives, you would need the quotient rule. This one, we can actually do without the quotient rule. Because I just am dividing by x squared, I am going to divide each piece by x squared. So I've got 3x to the 5th divided by x squared. And when we divide, we subtract exponents. negative 2x squared divided by x squared. X squareds would cancel, and I just get minus 2. And then I have plus 5 divided by x squared, which I can write as 5x to the negative second. And now the problem looks very similar to some other ones that we've done. We can add 1 to the exponent and divide by that guy there. What has a derivative of negative 2? Negative 2x. Add 1 to the exponent. Divide by that. And simplifying or rewriting here, 5 divided by negative 1 is negative 5. X to the negative first, we can move down to the bottom. So those are the 4 notes problems. I want you to try these 3 problems on your own. Go ahead and write them down in your notes. Show your work.